Welcome to AI Paper Slot. Today we are looking at a brand new paradigm-breaking paper titled Galaxia G0.5, one autoregressive stream for robot reasoning and action by the Galaxia team. And for those of you building in this space, here is the 60-second download.
Right, let's get into it.
So G0.5 is a new vision language action, or VLA, model built on top of Qwen 3.5 2B. And it directly challenges the current industry trend, where vision language models are sidelined as just, mere conditioning coders for separate flow matching action experts. You could think of architectures like Pi0.
Yeah, exactly.
But instead, G0.5 returns to a unified autoregressive stream. So a single transformer decoder generates both your reasoning and your continuous actions natively. The Galaxia team achieves this at foundation model scale through a learned cross-embodiment action tokenizer, a native chain of thought stream, and a highly efficient visual memory module.
And the results are just wild.
They really are. The results fundamentally alter the state-of-the-art landscape. I mean, it achieves an 82.5% zero-shot transfer rate on the DROID physical benchmark, and it completely dominates the behavior 1K long horizon benchmark using just a single policy checkpoint.
Honestly, that single policy checkpoint detail is the earthquake in this paper.
It really is, yeah.
Because we've spent the last year watching the embodied AI community completely bifurcate. Early autoregressive models, like the RT2 era, they tried to treat physical actions as text. But high-frequency, high-dimensional continuous control completely bloated the token context.
Oh, absolutely.
I mean, if your robot arm needs updates 50 times a second, discretizing every joint angle into standard language tokens just eats your context window alive. It completely destroys inference speed.
Okay, let's unpack this for a second.
Huh.
Because the token bloat was so bad, almost everyone pivoted.
Right, everyone moved away from it.
The standard playbook for the last 18 months basically became taking a powerful pre-trained VLM, freezing it, or maybe just lightly fine-tuning it, and then extracting its hidden states or key value cache.
Exactly.
And then you feed those embeddings into a diffusion or flow matching head. But when you do that, you fundamentally alter the role of the VLM. It stops being the core decision maker. It goes from being the actor to just being a very, very expensive visual sensor.
Which brings us right back to your chess grandmaster analogy, I think.
Yeah, imagine trying to teach a grandmaster to play physical chess, but you force them to wear a blindfold and only shout vague instructions to an intern who actually moves the pieces. That is exactly what the robotics industry has been doing to VLMs.
It's the perfect way to look at it, because the flow matching intern might be incredibly smooth at the physical mechanics of, sliding a chess piece across the board. But the grandmaster's deep strategic logic, the actual intelligence of the foundation model, gets bottlenecked by what they can convey through that restricted communication channel. And worse, it introduces a really severe anti-forgetting problem.
Right, because if you allow the gradients from that separate continuous action expert to flow backward into the VLM during training, you actively damage the VLM.
Yes, exactly.
Its pre-trained perception and reasoning capabilities actually degrade, because you are trying to force a continuous control loss onto discrete language weights.
Precisely. So teams started implementing what they call knowledge insulation.
Which is what, exactly?
It's essentially stopping the gradients or creating complex auxiliary tasks to preserve the VLM's original intelligence. But the Galaxia team looked at this entire trajectory and realized we were treating the symptom, not the disease.
Ah, I see.
Yeah, by siloing the VLM's generative reasoning behind a compressed conditioning bottleneck, the field was wasting the very in-context learning and logical deduction that makes foundation models so powerful in the first place.
So they just refuse to compromise.
Exactly. G0.5 solution is radical because perception, reasoning, and action all share the exact same next token cross-entropy loss. It all operates over one shared token vocabulary.
Wait, as an ML engineer, I'm immediately stuck on the physics of this.
Oh, sure.
Didn't the industry put the grandmaster in the box for a very good reason? If G0.5 is going back to an autoregressive structure, predicting actions token by token, how does it avoid hitting that exact same sequence length wall that killed real-time control in the earlier models?
What's fascinating here is that G0.5 doesn't just revert to the old style of tokenization. They realized the autoregressive architecture itself wasn't the problem.
Okay, then what was?
The naive tokenization of the physical world was the problem. Simply binning every degree of freedom at every time step is just highly inefficient.
Right, that makes sense.
So to make a unified stream viable, the Galaxia team had to invent a radically better way to compress and tokenize heterogeneous robot data.
And this brings us to their Cross-Embodiment Action Codec, which is honestly a masterclass in representation engineering.
It really is a massive breakthrough.
They took training data from 14 wildly different robot embodiment. I mean, we are talking single arms, bimanual setups, different grippers, some with mobile wheeled bases, some fixed to a table.
A huge variety of hardware.
Yeah, and they trained a codec end-to-end to map all of this chaotic physical diversity into a single, shared 27-dimensional unified action space.
And they achieved that compression by decomposing the robots into semantic parts. They created structural slots for left control, right control, grippers, and lower body.
Okay.
Then they processed these chunks using a residual vector quantizer, or RVQ.
Let's break down how that RVQ actually functions for you guys, because it's not just standard binning.
No, it's much smarter than that.
Think of RVQ as a multi-stage filter. The first stage captures the broad stroke of the arm movement. Say, moving the arm generally left by 30 degrees.
Right, the big movement.
Exactly. Then the next residual round calculates the error from that first stage and quantizes the correction. Each subsequent round refines the tiny sub-millimeter corrections.
That is the perfect way to visualize it. By layering these residual corrections, they can pack incredibly high continuous precision into just 8 discrete action codes per active robot part.
That's incredibly dense.
It is. And they also introduce a time contrast of loss during the codec's training.
What does that do?
Well, if a robot is performing a smooth sweeping motion over 3 seconds, you don't want the discrete tokens wildly fluctuating frame to frame.
Oh, because that would confuse the model.
Exactly. Inconsistent tokens create massive optimization noise for a VLM trying to predict the next step. So the contrast of loss forces semantically similar, temporally adjacent motions to stay tightly clustered in the token space.
But the real magic trick for saving the context window is their sparse active degree of freedom prediction.
Yes, this is brilliant.
If an embodiment doesn't have a lower body, or if the left arm is just sitting idle while the right arm performs a precision insertion task, G0.5 drops those idle parts from the token stream entirely.
It doesn't pad them with zero-value tokens at all.
No, it just entirely omits them from the sequence.
Right.
It's like a conductor who only cues the specific instruments needed for a specific measure, rather than forcing the entire orchestra to continuously read blank sheet music out loud.
And that sparsity saves an enormous amount of context window. It dramatically lowers decoding latency during live inference.
But I'm still a little skeptical about the precision here.
How so?
If you force 14 different robot morphologies into this single 27-dimensional vocabulary, aren't you inevitably losing spatial accuracy compared to a continuous flow-matching head that can predict exact floating point vectors?
You'd think so, but the empirical results show the exact opposite, and it comes down to structural alignment.
Okay, tell me more.
Because the RVQ handles the fine-grained precision, mapping a Franca research arm and a bimanual R1 Pro robot into the exact same semantic slots, actually acts as a massive regularization benefit.
Oh, I see.
This is precisely why the model generalizes so well across embodiments without needing per-robot adapters. The left arm of one robot speaks the exact same latent token language as the left arm of another.
Well,
Yeah, the policy learns a universal physical prior, rather than overfitting to the specific motor noise of one piece of hardware.
so because the action tokens are now highly compressed and context efficient, the transformer suddenly has the bandwidth to actually use its VLM reasoning capabilities in that very same token stream, mere milliseconds before taking a physical action.
Yes, and this leads to the native chain of thought integration.
Right.
Previously, teams would use a bolt-on controller where text reasoning was passed to an external system or generated in a completely separate forward pass.
Which is slow.
Very slow. But G0.5 interleaves the reasoning targets directly into the generative segment of the sequence. They use 4 self-describing targets: subtask text, B-box for drawing bounding boxes around key objects, trace for 2D gripper trajectories, and action hint for frame-level gripper state cues.
During pre-training, they sample from 8 different combinations of these targets, including a no-code baseline. And the critical point is that they apply the exact same next token cross-entropy loss to the bounding box coordinates and the subtask text as they do to the actual motor action tokens.
Exactly. To the decoder, it is all just one continuous language.
The zero-shot probe experiment they ran to test this architecture is incredibly revealing.
Oh, the air fryer one.
Yeah. They took a single G0.5 checkpoint and evaluated on 2 long horizon tasks on the R1 Lite platform, operating an air fryer and cooking bacon. And they set up an ablation where they could toggle the action head at inference time.
Right. They could use either the pure autoregressive action tokens, or they could route the hidden states to an optional flow matching head.
Here's where it gets really interesting. When they turned the chain of thought stream on, the autoregressive head's progress score jumped massively.
It was a huge leap.
Let's look at the cook bacon task, which is highly complex. It requires approaching the counter, grasping the bacon, placing it precisely in the pan, turning on the stove, and then flipping the meat.
Not an easy task for a robot.
Not at all. The AR head's success metric shot from 1.5 all the way to 3.4. But the flow matching head hardly benefited from the reasoning at all, only moving from 1.2 to 2.0. So is the VLM just generating worse reasoning when it knows the flow matching head is plugged in?
See, that would be the intuitive assumption, but the data proves otherwise.
Right, really?
Yeah, the researchers actually hand-scored the generated chain of thought traces for both setups. They found that both heads generated equally accurate reasoning, around 85% spatial and logical accuracy on the air fryer task.
Okay, so the reasoning was good in both.
Exactly. The bounding boxes were perfectly placed around the handle, the subtasks were logically sequenced. The massive difference in physical execution is purely structural.
Walk us through the mechanics of that structural difference.
In the autoregressive stream, the physical action tokens are emitted immediately after the reasoning tokens. Through the standard self-attention matrix of the transformer, those action tokens directly query and attend to the precise logical steps and bounding box coordinates generated just one token prior in the exact same sequence.
So the mapping is mathematically direct.
Exactly. The flow matching head, on the other hand, relies on a pooled summary of the hidden states. It usually takes a temporal or spatial average pooling of the VLM's context to create a conditioning vector.
Which means it loses the detail.
Right. The fine-grained token-to-token logical connection gets smeared into a general gist of the scene. The Grandmaster is shouting brilliant, precise coordinates, but the intern is only hearing muffled noise through the glass.
That structural bottleneck is a phenomenal validation for unifying the architecture.
Yeah.
But reasoning and acting cleanly at a single snapshot in time is only half the battle. Complex household tasks are inherently non-Markovian. Your robot arm swings across the camera, temporarily occluding the lens. You accidentally drop a spatula and have to replan. If your model only processes a single frame of vision, it is completely flying blind the moment the state changes unexpectedly.
And we know that naively stacking historical vision tokens into the context window scales quadratically.
Right, just explodes.
The attention mechanism balloons, which causes unacceptable latency when you are trying to output actions at 30 or 50 hertz. G0.5 solves this by injecting factorized spatial and temporal attention modules every 4 layers within the vision transformer backbone.
How does that actually bypass the sequence bloat?
Instead of concatenating everything into one massive flat sequence of tokens, it separates the operations. It attends to spatial patches within a single frame in one layer, and then sequentially mixes information across time steps in a separate layer.
Oh, that's clever.
Yeah, it builds a multi-second visual history without exponentially expanding the token length the decoder has to process.
For any of you who have ever tried to run a live ROS node on a physical robot, you know the absolute terror of a camera buffer dropping a frame.
It's the worst.
It really is. If your temporal history gets corrupted, your whole sequence crashes. The researchers knew this, so they implemented a really aggressive training trick. They stochastically drop all historical frames 30% of the time during training.
Which sounds counterintuitive at first.
Right, if you're building this, you might worry that dropping history prevents the model from learning complex temporal dependencies.
But that fear of dropped frames in the real world is exactly why they do the 30% dropout. It acts as a massive regularization technique.
How so?
If a model always has access to perfect, smooth temporal history during training, it becomes lazy. It leans on optical flow or temporal smoothing as a crutch. Then, when a camera glitch happens in the real world, it completely collapses.
It just doesn't know what to do.
Exactly. By forcing the model to rely solely on single-frame observations 30% of the time, the single-frame visual representations are forced to become incredibly dense and spatially robust.
That makes total sense.
Yeah, this dual capability, having a temporal memory but not being catastrophically reliant on it, pays off heavily when we look at the mobile manipulation benchmarks.
So we have this elegant architecture that solves the memory bloat and the reasoning bottleneck in theory. But the real test of a physical prior isn't in a pristine lab environment. How does it handle the noise of an unstructured household?
That's the real test.
Let's talk about the Behavior 1K benchmark.
Okay.
For those who don't know, this is a brutal 50-task household mobile manipulation suite. These episodes average over 6 minutes long, requiring complex navigation paired with bimanual manipulation.
And the results here are definitive. G0.5 achieved a 31.4% success score using just one policy checkpoint trained for 4 epochs.
Just one checkpoint.
Yes. To put the magnitude of that into perspective, the competition winner for that benchmark required an ensemble of 4 distinct checkpoints, heavily customized for different task clusters, just to hit 26.1%.
And the training speed is equally staggering. After just one single epoch of post-training, G0.5 hit 29% success.
Wow.
That one epoch alone beat the Pi 0.5 model that had been trained for 4 full epochs.
That training efficiency is a direct testament to the quality of the pre-trained backbone. When your tokenization is semantically aligned and your continuous action space doesn't fight your discrete language space, the model absorbs downstream task data incredibly fast.
Right, the foundations are solid.
Exactly. The representations are already primed for physical control.
We see that same robustness on the DROID real-world physical benchmark.
Yeah.
DROID tests zero-shot transfer to held-out environments and completely unseen object instances.
The hard stuff.
Exactly. G0.5 scored an 82.5% success rate, while the Pi 0 baseline was down at 57.5%. And we aren't just talking about picking up standard blocks. This benchmark includes tasks like differentiating a deformable carrot plush from a rigid peach.
Which is super difficult for a robot.
Yeah, that requires deep visual triers because the grasp physics for a soft, squishy object are entirely different from a hard sphere.
The pick-and-place benchmark also isolated an incredibly futuristic capability. At the 50-hour post-training scale, G0.5 demonstrated zero-shot prompt-driven action steering.
Okay, the language steering completely blew my mind.
It's amazing.
They showed a scenario where the baseline prompt was, pull the drawer open by the top dial. If the robot failed to grasp the dial, the engineer didn't have to retrain any weights or provide kinesthetic demonstrations.
Right, no new data needed.
They just edited the text prompt to lower handle. The model dynamically shifted its physical policy to reach for the lower handle instead. It is natively linking the semantic text tokens to the spatial action coordinates in real time.
And because those action tokens are discrete, autoregressive outputs, it unlocks another massive advantage for engineers: reinforcement learning readiness.
Let's expand on that. Why is an autoregressive model inherently better suited for RL than a continuous diffusion model?
Well, it comes down to the math of policy gradients. To apply reinforcement learning, you need to calculate the exact probability of the action the model just took.
Right.
Autoregressive models natively output exact token-level log probabilities for every step. You can take a modern RL algorithm like Group Relative Policy Optimization GRPO and apply it right out of the box.
Oh, that makes it so much easier.
Exactly. The authors demonstrated that the AR policy converges much faster and to a higher optimum than the flow matching head. Applying RL to a flow matching model requires incredibly complex stochastic differential equations just to approximate the policy likelihoods. With AR, it is just native, highly optimized cross-entropy math.
It's important to note, though, it wasn't completely flawless. The paper specifically details a weakness when the robot was dealing with a semi-transparent drawer cabinet.
Ah, yeah, the clear plastic issue.
Yeah, the model's success rate was quite low until the researchers explicitly added high-contrast orange adhesive markers inside the drawer, at which point the success rate jumped to 100%.
Which is a very telling detail.
It is a vital reminder for practitioners. An autoregressive architecture, no matter how elegant, cannot fix inherent sensing limitations. If the vision tower cannot confidently resolve the spatial geometry of a clear plastic object, no amount of downstream logical reasoning can hallucinate the correct motor control. It doesn't fix bad photons.
That's the core of the issue. The physical prior is vastly improved, but it is still fundamentally bound by the visual acuity of its encoder.
So what does this all mean for the field? When you look at the fact that a single G0.5 checkpoint beat a 4-policy specialized ensemble on a 50-task benchmark and generalized to soft versus rigid objects zero-shot, well, it means the large-scale pre-training actually succeeded.
It really did.
We are definitively moving past the era of training a specific, bespoke policy for every specific physical task.
If we connect this to the bigger picture, G0.5 proves that large-scale web data co-training, combined with direct autoregressive action supervision, protects and enhances the underlying foundation model.
Exactly.
It proves the VLM shouldn't be sidelined. When allowed to be the primary actor in a unified stream, it yields faster training, deeply integrated language grounding, native RL compatibility, and massively superior long horizon planning.
It is a complete paradigm shift.
Oh.
And I want to leave you with a final thought to mull over. G0.5 proved that you can alter a robot's physical kinematics just by changing adverbial qualifiers or spatial cues in the text, prompt swapping top dial for lower handle, and watching the physical arm immediately adjust its trajectory.
Natively zero shot.
Natively. So if an autoregressive VLA natively connects semantic language to physical action this cleanly at just 2 billion parameters, what happens when we scale this unified architecture to 70 billion parameters or more?
That's the million-dollar question.
Are we approaching a threshold where we won't debug a robot's physical failures by tweaking Python code or reward functions, but simply by debating semantics and spatial logic with it in real time?
The barrier between natural language and physical manifestation is dissolving entirely.
It really is.
Yeah.
That wraps up this deep dive into the source material. Thank you for listening to AI Paperslop, and we'll catch you next time.